All right, today we're talking about a piece of tech that is, quite literally, an invisible giant. It's everywhere, powering massive factories, but also hiding right there in your kitchen counter. We're going to pull back the curtain on the powerful and, beautifully simple asynchronous motor. So, to get us started, here's a fun one for you. What on earth does a game-changing electric car have in common with that blender you use to make smoothies? Well, the answer is the exact same core motor technology we're digging into today. It's a pretty wild connection that shows you just how fundamental this thing really is.
Okay, let's get right into it. When Tesla first burst onto the scene with the Model S and Model X, they made a really interesting choice. They didn't use some brand new futuristic motor. Nope. They used an old school industrial workhorse, the AC induction motor, which is just another name for the asynchronous motor. We're talking about a design that had already been reliably powering the world for over 100 years.
So how does this thing actually work? Honestly, the best way to picture it is as a constant, never-ending chase. You've got one magnetic field that's always running and another one that's always trying to catch up, but it never quite gets there. And that chase, well, that's where all the magic happens. The secret is right there in the name, asynchronous. It literally means not in sync. So you have the part that stays still, the stator, and it creates a spinning magnetic field. Then you have the part that actually spins, the rotor, and it gets dragged along for the ride. But here's the key. It always lags just a little bit behind. It's never perfectly in sync. And as you're about to see, that's the whole point.
Let's just break it down into 3 simple steps. First, the stator uses electricity to create the spinning magnetic field. Think of it as the runner. Second, that spinning field creates or induces a current in the rotor, giving the rotor its own magnetic field. And third, and this is the crucial part, the rotor's magnetic field starts chasing the stators, but it can never, ever fully catch it.
But hold on, how do you make a magnetic field just spin around in a circle using nothing but electricity and some wires? I mean, it sounds like something out of a sci-fi movie, but it's actually an incredibly clever trick using standard 3-phase AC power. Let's see how they do it.
So just picture 3 sets of wire coils arranged in a circle inside the motor. First up, electricity flows through that first set, we'll call it phase A, and boom, it creates a magnetic field that pulls straight up. Simple enough, right? Now here's where it gets cool. Just as the power in phase A starts to fade out, phase B, the next coil in the circle, gets juiced up. So now the magnetic pole shifts. It's pointing diagonally to the right. You can probably see where this is going. And of course, just as phase B starts to fade, phase C fires up. This third set of coils yanks the magnetic field even further around the circle. It's like a perfectly timed magnetic relay race, with each phase handing off the pole to the next one. And this cycle, A, then B, then C, over and over, happens dozens of times every single second. The result is a perfectly smooth, continuously rotating magnetic field inside the motor. This is our runner in that great magnetic chase we were talking about.
Okay, now we're getting to the most brilliant, most counterintuitive part of this whole design. We've established that the rotor is always falling a little bit behind the magnetic field. Well, that little speed difference has a name. It's called slip. And it's not a bug, it's the entire secret sauce. So let me ask you this. What do you think would actually happen if the rotor, just for a second, managed to catch up? What if it perfectly matched the speed of that spinning field? What if the chase finally ended? The entire motor would just stop working. I know it sounds weird, but power is only generated because there's a difference in speed. If the rotor ever caught up, from its perspective, the magnetic field wouldn't be changing anymore. No changing field means no induced current, and no current means no torque, no power, nothing. The chase absolutely has to continue. Let's put some real numbers on this to make it clearer. The magnetic field might be spinning at a perfect synchronous speed of, let's say, 3,000 revolutions per minute. But the actual rotor, the part doing the work, it's spinning just behind, maybe at 2,850 RPM. That small gap, that 150 RPM difference, that's the slip. And that's what makes the whole thing go. So this clever, self-regulating design isn't just a neat little physics trick. It's the very reason the asynchronous motor became an absolute superstar of the industrial age. Let's take a look at why it ended up being the go-to choice for, well, almost everything. Here's the winning formula. The design is just dead simple. There are no brushes or other physical contacts that can wear out, which makes them insanely durable and super low maintenance. And, all of that adds up to one very important thing. They are cheap. Really cheap to build and to run. And that's why you find them in everything from giant factory conveyor belts to pumps, fans, and yeah, your kitchen appliances. So let's bring this all the way back around to where we started, the electric car. If this motor is so tough, so simple, so reliable, why are some car makers, including Tesla and its newer cars, starting to use different designs?
Well, like with everything in engineering, it all comes down to trade-offs. As you can see, the asynchronous motor is cheaper, and, this is a big one, it doesn't need expensive and pretty controversial rare earth materials to make its magnets. But there's another design, the permanent magnet synchronous motor, or PMSM, that can offer slightly higher peak efficiency. And when you're talking about an electric car where every single mile of range counts, sometimes that little efficiency gain is worth the extra cost and complexity.
But even with these new technologies showing up, the asynchronous motor is not going anywhere. Its legacy is totally secure. Its real power comes from that perfect marriage of elegant, simple physics and an incredibly tough, reliable design that just works, decade after decade.
And that kind of leaves us with a final thought to chew on. As we're designing the machines of the future, what do we value more? Is it all about raw, absolute peak efficiency, no matter the cost, no matter the complexity? Or is there an enduring, maybe even greater, power and elegant simplicity? That's a question engineers are going to be wrestling with for a long, long time to come. Thanks for joining me.